for this particular problem, it's just a 4 kilogram block is released from rest at the top of a frictionless incline that has a height of 10 meters. And then here, part A, it asks us to calculate the speed at the very bottom of the incline. Part C asks us to find the time it takes to reach the bottom. And then part C wants to find the magnitude of the acceleration of the block. So we know that it's going to pick up speed as it slides down the ramp. Okay, so it is going to accelerate. All right, so here's the diagram. H being 10 meters, the angle of the ramp or incline here is 37 degrees. Keep in mind it is frictionless, so this is a conservative system, meaning there's no energy loss due to friction at all. All right, so one of the ways to find part A is to use conservation mechanical energy. I can apply this because this is a conservative system. I want to take my initial as the very top of the incline. I want to take my bottom, or my final is at the very bottom of the ramp. So at the top of the incline, there is potential energy and there's no kinetic. And then at the very, very bottom, there is only kinetic and no potential. But I will go ahead and expand these, the two sides here based on what it should be. Mechanical energy is potential energy due to gravity plus kinetic energy. And then likewise on the right side, except one side is initial, one side is final. But as you notice here, it says release from rest. So PE stays, KE disappear. KE disappear because the initial speed is 0. On the right hand side, PEF is going to disappear because at the very bottom of the ramp, there is no height. Because there's no height, there is no PEF. So really, this particular function simplifies down to just PEI must equal to KEF. What that means is that the potential energy at the very, very top of the ramp converts all of it to the to kinetic energy at the very, very bottom of the ramp. Okay, so these are two extreme points at very, very top and very, very bottom. So I can expand PEI into MGHI. I can expand KEF into 1/2 MVF squared. But as you can see here, mass appears on both sides. So I'm actually going to go ahead and cancel that out as well. So to get VF squared by itself, I will multiply both sides by 2. Or you can just move this 2. Excuse me. You can just move this 2 in the denominator on the right side up to the top left numerator. So by doing so, you have 2GHI, which is equal to VF squared. At this point, in order to get VF by itself, you got to square root both sides. So there it is. Taking the radical of the right side gets rid of the exponent 2 here. All right, now that we know everything, we know I'm just going to carry down the 2, and we know G is 9.8. We know the initial height is given as 10, because in the diagram here, H is 10 meters, and so that's just it. All right, so all you have to do is punch in a calculator, and 2 times 9.8 times 10, which is 196, and the square root of 196 is 14 meters per second. And because it says speed, I do not need to give any sort of direction. If it does say velocity, you can say 14 meters per second down slope, okay, if you need a direction. But here it says speed, so I will just give you the magnitude. So the answer to part A is 14 meters per second. All right, let's go ahead and do B. Part B asks you to calculate the time it takes to reach the bottom. Well, there's a bunch of different ways to do this, okay? I'll show you a couple ways, and then hopefully you do whatever you want. Here, I think the easiest way for me is I recognize that this is the information I'm given. Here, it has to find time, so time is my unknown. I know what VF is, which I just calculate, which is 14, and then VI is 0 because it starts at rest. I don't know what delta x though is. Okay, so I'm using this because from the diagram I can find delta x quickly, which I'll show you how to do in just a second. So I'm using this first approach because it's the easiest way for me to do. All right. However, in order to solve for time, you notice here on the left side, t is in the denominator, so you need to get it to the top. So what I want to do is I'm actually going to flip the functions upside down. So I want to flip both sides. Okay. Therefore, delta t is going to go up. Delta x is going to go down, the 2 on the right side goes up, and then VF plus VI go down on the bottom. And then from here, I can just cancel out VI because VI is 0, almost there. To get delta t by itself, I need to get rid of this delta x by multiplying both sides, so it's going to look like this. Or I can just move delta x up and multiply that by 2, which is what I'm doing, okay? So delta t is equal to 2 delta x over VF. Well, we know what VF is, right? We found VF is 14 already. We don't know what delta x is, though. Well, delta x here, I like to point out, is the length of the ramp. So do not have the misconception. Sometimes folks might want to find like the base of this triangle, which is, x, but that's not how the box is moving. The box is moving along the surface of the ramp. Therefore, we take the surface of the ramp to be our delta x because that's how the box is moving. So make sure you find the right x when you calculate stuff so that you're not getting in trouble. All right, so the surface of the ramp is my delta x because that is the direction and the motion is in. Okay. So to find delta x is pretty easy. For this particular right triangle, you're given an angle of 37, and you're given a leg here of 10. So as long as you're given enough information, you can find the rest of this missing right triangle. Okay. So here you're given an angle, you're given the opposite, so, and then you're trying to find the hypotenuse. Delta x here being the length of the ramp, which is the hypotenuse in this case. So I am going to use sine. Sine of 37 degrees is equal to opposite over hypotenuse. And that's the definition of sine mathematics, right? Again, sine of 37 degrees is equal to opposite, which is 10, divided by the hypotenuse, which in this case is delta x, which is the length of the ramp. So therefore, in my work, I have sine of 37 degrees is equal to opposite, which I call h, divided by the hypotenuse, which is delta x in the diagram. Well, here to find delta x, all I have to do is switch delta x up to the top left numerator, and then move sine 37 down to the right denominator. Here, to solve for delta x, I just need these two things. I need sine 37 is just a number on your calculator, and then h is known, it's given in the diagram. And so therefore h is 10, so I'm just going to plug and chug. H here being 10, and then divided by sine of 37, and you will get about 16.62 meters. Okay, so that's that. So delta x here is 16.62 meters. So which makes sense, right? The opposite leg is already 10, so the hypotenuse has to be longer than 10, which is 16.62 in this case. Well, now that I know delta x, I can just plug it back into my delta t function. So I'm just going to carry this delta t function down. 14, I mean, we know 2, we're missing delta x. We know the denominator is 14 because we found that in part A. So therefore, all I have to do is substitute. Delta t is 2. And wherever delta x is, I can just substitute in for 16.62. The denominator is 14, so I can just leave that alone. So if you simplify this on your calculator, you'll get about 2.37 seconds. So that is the answer to part B. Okay, so that's the first way. That's how I would do it, only because the problem gives you pretty much the entire information, especially if you're using the information from part A that you just found. So why delta x is not directly given to you, you can find it pretty easily because if there's enough information to find delta x, or the hypotenuse of the right triangle in this case. All right, the second way to do is this. All right, I'm still in part B. It's just calculate the time. So what if you were to use the average acceleration equation? All right, there's different ways to do this. I'm just saying, what if you had started with this, because it has a delta t in it, because ultimately the question is that's asking for delta t. Well, here, if you started with A is equal to VF minus VI divided by, changing time, hopefully recognize that because delta t is on the bottom, you can just switch A and delta t. So the denominator, delta t, is going to go to the top left, and then A is going to go down to the bottom right. So really, you're doing multiply by delta t and dividing both sides by A at the same time. So I'm just going to go ahead and cancel out VI because VI is 0. So here, delta t is just VF divided by A, right? Well, I know what VF is, right? VF is 14 from my previous work, but I don't know what A is. So once again, here you have an unknown. Just like the previous strategy, you're going to run into unknowns, and it's your job to kind of, untangle these types of problems. Well, I don't know what A is, but I can go find A. Well, how do you find A? I can use this kinematics equation. Why? Because I have VF, I have VI, I just found delta x in my previous work. So the length of the ramp is found to be 16.62. So if you need to rewind the video, all I did was I did sine of 37, which is equal to opposite over hypotenuse to find delta x. So to find A is super light work. Okay, so here I'm going to cancel VI because VI is 0. And then to get A by itself, I divide both sides by 2 and delta x, or I'm just going to move the delta x down to the bottom left. I'm also going to move delta x down to the bottom left. So therefore, VF squared divided by 2 delta x equal to A. Well, we know VF is 14. We know delta x, which we already calculated, is 16.62. So here we just do 14 squared, which is 196, and then divided by 2 times 16.62. And if you do that correctly in the calculator, you should get an acceleration of about 5.9 meters per second squared. Well, you're kind of done, right? To find delta t, you needed two things. You have a VF, you didn't know what A is, you just found A. So I'm just going to carry my work down from here to here. So delta t is simply 14 divided by A being 5.9. And if you do that correctly on your calculator, you should get a value of 2.37, okay? And now, I do want to point out though, if you did it this way, you actually found the answer to part C as well. Because part C asks you, what is the magnitude of the block's acceleration? You just found it here as 5.9. So depending on which strategy you use, you might find the answer to different parts before you're even done, okay? So I want to emphasize, if you had taken this approach, you would have been stuck with A. You would have had to use this kinematics equation to find A. but finding A, you found the answer to part C. Well, the answer to part C will help you find the answer to part B if you had taken this route. All right. But the point is that you get 2.37, which is the same answer. All right. So whatever it is you want to do, just make sure it works out. However, I do want to point out that if you have any experience with incline problems, okay, then if you don't, you can learn something here. Well, here's the ramp. For incline problems, we like to take our surface, the length of the ramp, as our x-axis, right? As I stated earlier, we treat the surface in which the object is moving in to be our x-axis. So you notice here I just drew an arrow, and this is going to be my x-axis. Well, my y-axis is going to be perpendicular to that, okay? So make sure you draw your y-axis correctly, because when x tilt, y has to tilt with it because it has to be perpendicular to each other. Well, here, this is the weight of the box. The weight of the box would be pointing down the page, which is f of g. Okay, regardless of how you tilt your axis, the vector for weight will always be down the page. Well, here f of g lies in between the y-axis and the x-axis, which makes it a diagonal, right? The hypotenuse. So you can turn this into a right triangle. The f of g component that just came up, that is along the y-axis, so we call this f of g y. And then there's another component that's pointing down slope that's parallel to the x-axis, which is f of gx. Once again, if you have any experience with incline, hopefully this makes better sense. If you don't, feel free to, keep watching or just stop. But if you know this, then fgx is pointing down the ramp, which is along the x-axis, is parallel to the x-axis. So all you have to do is really just carry this 37 degrees. See this angle of the ramp that's given as 37? It is also the same angle right here where my cursor is at, that lies between the f of gy and f of g. So if this is 37 degrees, that will also be 37 degrees. So I'm going to go ahead and label 37 degrees. Well, now all you have to do is do a little bit of geometry. Okay, I can just set up Newton's second law. Net force is equal to mass times acceleration. Well, the object accelerates down the ramp in this case, which is along the x-axis. So I'm just going to focus my attention on the x-axis here. Well, what's causing this box to slide down the ramp? It's f of gx. F of gx is pointing down the slope, okay, which is the force component that is responsible for accelerating this box down. Well, here, f of gx is equal to max. I can expand f of gx into mg sine of 37. Okay, notice the right side hasn't changed because it's still mass times acceleration in the x direction. Now, mg sine 37 comes from, if you reference this angle here, this is angle 37. If you look across, this is f of gx, which is your opposite. Your hypotenuse in this case is f of g. So therefore, we say sine of 37 is opposite, which is f of gx, divided by the hypotenuse, which is f of g. And if you solve for f of gx, you'll get mg. Excuse me. You'll get mg sine of 37. But as you can see here, mass appears on both sides. Therefore, they will cancel out. G being 9.8. And then sine of 37 is just some number on your calculator. And if you simplify this on your calculator, you get a value of 5.9, which is the same answer that I found earlier using kinematics. Okay, so you can stick to kinematics, or you can apply your forces for an incline, and it should all work out the same. All right, I hope that helps. Stay in there, don't be white.